So hi everyone, thanks for joining the session today. We're going to talk about liquid cooling, what I think is going to happen over the next 3 to 5 years, the way we at HPE think about rack density and which products kind of fit different categories, and why liquid cooling generally, one size does not fit all. So the one thing I always like starting with is just kind of setting the stage. What's happening in the industry? What are some of the things that we're thinking about? But what are some of the elements that are affecting adoption rates for liquid cooling? When we look at chip density, a lot of this isn't new. We're seeing really exciting new chips come out from all of our chip vending partners, and power is going up. CPUs are quickly going beyond 500 watts and GPUs beyond 1,000 watts. And so rising TDP, or thermal design power, is one part of the equation. But the other part of this is their tolerance for heat overall. The one part of this that we don't always talk about a lot is decreasing T-case, or the thermal case temperature tolerance at these chips. A lot of them, anything that's a super chip or any kind of new innovation we're seeing where there's a lot packed into one socket, means it's probably not going to be very heat tolerant. And so air cooling some of these chips might not be an option in the future. And so we're constantly thinking about how are we packaging this new technology in air-cooled boxes versus liquid cooling, and which ones may only get a liquid-cooled option. And we'll talk a bit about that today. Now, the value proposition for liquid cooling has really been always about, for the last several decades, the top of this triangle, performance. We run supercomputers very hard for long periods of time with top bin processors. When we look at El Capitan, Frontier, Aurora, all of these big exascale supercomputers, they're all liquid cooled. And the reason we do that is because there's no throttling. We can run them at very high densities for long periods of time. But the other part of this that's starting to get more traction and more interest globally is the efficiency part of the story. If we can majorly decrease the energy costs inside the data center because we're shifting to a liquid-cooled strategy versus air cooling, that can be quite attractive. And we're starting to see new legislation and new mandates come from governments around the world starting to dictate what facility air temperatures are allowed, warmer and warmer, as well as facility water. And so we're starting to see some of that be affected. Now, the other part of this is around density. If we can fully populate racks, think about many of the data centers you've seen today, a lot of them are a third, maybe a quarter populated for power and density and cooling reasons. There's a lot of that data center space that's being wasted. What if we fully populated those racks? We could build smaller data centers. We could bring all the connectivity much closer. A lot of that's enabled by liquid cooling. So this is kind of the way I talk about liquid cooling, the major value props, and what drives it today. Now, what I really like doing is breaking this up into very real world terms, real rack densities. What are you dealing with, and how are we breaking this up with different cooling technologies? When we look at this graph, globally, most of the servers out there are below 10 kilowatts, but this is the entire data center industry globally. Where we play with liquid cooling really is in the second half. And what we're seeing is a migration towards higher rack densities year over year. And a lot of this is going to then really perpetuate the need for liquid cooling for AI, enterprise, and HPC workloads. And so again, one of my major objectives today is I want to really demystify where is liquid cooling really useful and applicable, and where does it not make sense. Don't bother investigating technology in this space. Now, the first bucket, I think, is always an easy story to tell. Under 10 kW, to me, is not a place for liquid cooling. Whenever we talk about liquid cooling, it's performance, density, energy efficiency, but with liquid cooling comes some less options. And so in this space, this is where there's a few ProLiant servers in a rack. You want maximum flexibility. We don't want to have to put a CDU or a coolant distribution unit in there. We don't want to do anything with rear door heat exchangers. We can usually just air cool that just fine. And so again, you get a lot of flexibility. This is most of our standard offerings for ProLiant, and some of what we do in HPC. Now, as we go higher up the stack, we start talking about innovations in the server. So this is a cooling range from, again, I make a lot of blanket statements because I want to leave you kind of really easy information to take away, is between about 10 and 20 kilowatts. This is where we start to see maybe a single 8-way GPU AI box in a rack, or maybe a half rack of ProLiant servers. What we start doing in this space is some closed loop liquid cooling. Because really, we need a little bit of a performance bump thermally at the server. So sometimes we put radiators inside the servers with a little cold plate, moving coolant around. or we build bigger boxes. That's really the way that we do this with this technology. But where we really start talking about liquid cooling is in this 20 to 40 kilowatt range, where we need a lot of flexibility, but we also are starting to encounter a lot of thermal issues in the data center. And so this is a nearly full rack of servers, or a handful of AI or HPC boxes in the rack. The technologies we start talking about are liquid-to-air coolers. So we still need facility water, like direct liquid cooling, but we're actually using it just to create cool air very close to the IT. So if you're familiar with perimeter cooling in the data center, or even in-row coolers, most of them are taking facility water into a coil and creating cool air. What we're doing is taking that facility water and driving it directly to the coil, very close to the IT. So it's much more energy efficient and thermally effective than perimeter cooling, but now we're bringing that cooling really close to the IT. The big positive about these products is they're more energy efficient than perimeter cooling, but they still give you tremendous flexibility. What you put in these racks can be compute, AI, networking, even storage. We can cool almost all of it inside of these racks. So now, let's talk about some of the bigger applications. When we start to move in this range, this is where the line becomes a little bit less gray to me, where liquid cooling fits really well. Though you can do a lot of interesting things, in the 40 to 50 kilowatts with a data center that's well optimized for air cooling, it becomes difficult. Liquid cooling does really well beyond this range. So 40 to 70 is where we do a lot of work with direct liquid cooling in ProLiant, Cray XD, and even in our supercomputers, Cray EX. These products, and for really kind of general education, whenever we talk about direct liquid cooling, include cold plates. So instead of the aluminum air-cooled heat sinks that are mounted on the server for a normal air-cooled server, we're replacing those with these copper Skyfin cold plates. So we're taking liquid, pumping them directly into servers. It's capturing all that heat, pumping it back to one of these CDUs. In this case, this is a 4U CDU mounted at the bottom of the rack. It interfaces the heat through a plate-to-plate heat exchanger, and all that heat ends up going back to the facility. So you can imagine each one of these racks is plumbed directly to a facility water loop, and it's taking all that heat away. Now, what you're seeing on the server is pretty typical. We liquid cool the GPUs, CPUs, sometimes NVLink, sometimes memory, but we don't touch everything. And that's part of that flexibility strategy. We want to take the majority of this heat away with the components that are very rinse, repeat, socket sizes, and form factors don't change a lot, but the rest of the components on here can. And so we take the heat away from the big components, but we let you pick what are the other parts we need. NIC cards, different networking. We intentionally aren't liquid cooling that because we don't need to. Now the other part of this, I always like kind of educating and sharing, all the little pieces about liquid cooling are the different types of liquid cooling for CDUs, or coolant distribution units. So there's really two ways that we do this. One is where we take a really big CDU, which is shown on the right, and we have really big pumps, and we cool a really big cluster of racks. Now the pro of this is, we can often ship these CDUs to the data center in advance, or colos may deploy some of this technology in advance. So when you go into that space, it's already kind of set up for you. The cons is often this cluster needs to be the same. The CDU often can't tell the difference between a high density AI system and a CPU system, and they require different flow rates, sometimes different temperatures, and often, even from a failure domain, they're all linked together. So there's pros and cons of both. When we look at in-rack CDUs, you can imagine each one of these racks is a completely standalone system. So it has an in-rack CDU, these are 4U CDUs. They provide all of the cooling for that one rack. Now same kind of inverse trade-offs. The pros are each of these racks are standalone. They can be all different technology. They are single failure domains, so one rack doesn't affect the other from its coolant, any kind of hardware issues. But the biggest pro is these entire systems can be pre-built, rack and rolled. So we build up this infrastructure in HPE facilities, completely cable them, fill them with coolant, and we'll do all of our benchmark testings. So when they're shipped, they're in a single crate. We take off the door, roll it onto the data center floor, hook it up to power and water, and they're ready to go. They need a lot less assembly than some of these bigger systems. Now the other part of this is, kind of what are the different loops, kind of for bringing folks up to speed on the terminology we talk about with liquid cooling. There are always two water loops that are happening in this infrastructure. The main primary side loop is what the building is responsible for. So this would be your data center, the co-location, this is what they're managing. It's almost always water with some kind of inhibitors, right? They don't want any weird stuff to grow, but they have a big reservoir somewhere in the building, big pumps, really big 4 to 8 inch pipes running throughout the facility. That primary side water is being plumbed directly to the CDU. So in the big CDU case, we have a single facility water connection. In the in-racks, we'll plumb it to each one. And why this is important is it allows us to run the secondary side, which is a different fluid. We standardize on 25% propylene glycol. PGW is extremely resilient. Has biogrowth protection, corrosion protection, even has freeze protection because we do all of this rack and rolled. We ship systems full. And we want to ensure that these systems run long-term, highly reliably. Now the other part of this is we always get questions about intercompatibility and standardization. It's important that all of this liquid-cooled infrastructure, when it's going into a data center, isn't including really weird connections. So when we're thinking about deploying multiple vendors in one space, that we're really using standardized stuff. And the reality is, every one of these CDUs really has very standard sanitary flanges and tri-clamps. So if you've ever been inside of a brewery and you've seen all the stainless steel connections, it's all food safe. Those are the same types of connections we're using here. Food grade, highly reliable, standardized connectors, so you could deploy any kind of liquid cooled technology in the data center, and it's almost always using these types of connections. So from a multi-vendor strategy, it's very easy to deploy this. Now, when we talk about the high end, and this is always kind of very interesting because the world we're in now, this used to be just HPC supercomputing, x86 stuff. But where we are today is this is starting to include some of the AI applications. We're starting to see 100 kW racks enter the space, and we have to have an effective liquid cooling strategy for them as well. So this would be a full rack of HPC servers, fully loaded with 8-way GPU systems, and much of what we do with Cray EX. At this space, we often see the demand and requirement for 100% liquid cooling, or at least 100% heat capture to liquid, and we do this in 2 different ways. One is we often will combine direct liquid cooling, which is the liquid cooling to the server technology, with liquid to air cooling, like ARCs or rear door heat exchangers. So if we have, let's use kind of simple round numbers for this example, we had a 100 kilowatt rack. 70 kilowatts would be going directly to liquid for the direct liquid cooled system. 30 kilowatts would be going to the rear door heat exchanger or ARCs, but all of that heat ends up in the facility water loop. So when the data center is looking at this from a thermal perspective, this really has a 0 footprint from the cracks and craws around it. They have no thermal footprint because this is all room neutral and the liquid cooling is taking all the heat away. The other way we do this is with 100% liquid cooling at the cold plate level. This is everything we do in Cray EX and our supercomputing platforms. When we deploy this technology, it is amazing how quiet these racks are. We could be talking at this volume, and there could be over 1 megawatt of compute running within a few feet, because it's just pumps moving the coolant around in a very passive way, but very thermally effective. And so a few ways that we do this technology. Now the other part of this is why HPE? We've been doing this for a long time, but it's important that we have the right mix of products and we have the right experiences to bring to customers around the world. Now across the portfolio, we really do this everywhere. We have always done by default full liquid cooling in our Cray EX supercomputers. In our Cray XD HPC, which is AI and classic HPC, most of our products have liquid cooling. And ProLiant is also leaning in heavily, offering enterprise grade, enterprise availability liquid cooling. Now the nice thing is, kind of everything in the middle here is cross-compatible. So as clusters are built, we can build HPC networks and have all of the support node infrastructure also being liquid cooled. With direct liquid cooling, liquid to air cooling, there's a lot of availability between all the segments. And we've been doing this for a really long time. So the footnotes I always really kind of proudly talk about is, in 2017 we acquired SGI, 2019 Cray, and HPE has always been doing liquid cooling. And so we often get questions about, well, why single phase direct liquid cooling with propylene glycol? Why not do this technology? Why not do that? And for the most part, we have validated and tried almost every technology on the market. Immersion, two-phase cooling, refrigerant cooling, and we continue to promote and invest in single-phase propylene glycol direct liquid cooling because it's so robust, it's so reliable, and it's so thermally effective. Now the paths to get liquid cooling in here, right? You're seeing all the interesting hardware, you're seeing this liquid cooling future, but the question I often get is, okay, Jason, now what? So what? How do we actually get this technology in-house? Of course, retrofitting is one of the paths, but I find this is not very common, to be honest, that data centers get completely gutted and have liquid cooling added, because often those data centers still have a use with their current air cooling workloads, the data center infrastructure they want to use. More often what I'm seeing is the investment in the new data center, new white space optimized for direct liquid cooling, modular data centers where HPE builds the entire infrastructure, rolls it into your parking lot, and we plug in a full liquid cooled computer, and co-location data centers. This is one of the areas we're seeing a lot of investment in, where colos want to differentiate and have high power and liquid cooling availability ready so that we work with them and deploy this technology seamlessly without you having to figure out in-house where does this stuff go. Now, I always like talking about actual use cases, real customers that have deployed this technology, kind of how and why. Last year, we deployed one of the world's largest AI supercomputers in the UK at the University of Bristol. This was a completely containerized AI supercomputer, 100% liquid cooled. It also had a very short timeline. From signage to system turn on was under 1 year. I think the number was pretty close to 8 months. And so for speed to market, especially for organizations that are looking to advance their AI strategy quickly, with hardware that's changing quickly, you need a partner that is time to market ready, but can also physically move the stuff to your data center. And in this case, we built the data center and shipped it to them. Other customers we've worked with in the past, this is an interesting one as these customer types are looking to incrementally increase their HPC capabilities. They want to start using the latest and greatest CPUs and GPUs, but they need a flexible strategy from the hardware perspective. And so rear door heat exchangers and ARCs, where we're taking mostly air-cooled servers, but we're using really effective thermal solutions, have a lot of goodness for them. They do some DLC, but we've also done a lot of these liquid-to-air solutions. Colos. This is one where, again, we're seeing a lot of increase in the data center, and there's been a few interesting examples where we have used ARCs for a lot of this flexibility with DLC. So in the co-location data center, they're doing 100% heat capture of high-density racks besides some lower-density enterprise racks. And again, because they're fully contained in these ARCs racks with DLC, it's not changing the thermal dynamic in the data center. It's all being contained. But again, it still gives them a lot of flexibility. Now, the last part of this, to me, I think is where I always pause and I really try to emphasize the story. Where this stuff is built and how it is built really matters. We have, for several decades, been building the world's largest supercomputers that are liquid cooled, manufactured in the US and in Europe. And this capability has really been reinforced by the teams that we have, but the actual infrastructure. You can imagine, again, we talk about, it's been getting lots of press, El Capitan. These systems are 30 megawatts. Those systems had to be built somewhere, and they had to be brought online. And so those are not single cabinets at a time. They're large clusters of over 1 megawatt. And so our mentality has always been to invest in and bolster our manufacturing capabilities so we can build world-class programs and products, but also often have customers come and see those products. Because much of them, because we're doing benchmark testing, we involve the customers. So this is part of that liquid cooling story. If you think about liquid cooling, it's often also high density HPC or AI systems where they cost more because they're bigger systems, so the customers are more involved. And it's important that we have facilities where we can do that directly with our customers. And again, completely rack and roll. So these systems are pre-tested, single crates shipped to customers, they're ready to plug in. And the last part of this is around service. So this technology is, aside from some HPC customers, is very new, and that's something we recognize, that customers are going to need a beginning to end collaboration with HPE on the system design, facility review, performance contracts, but even what is going to be the coolants and maintenance check plan. Now, still relatively simple, air-cooled stuff. The building needs to manage the humidity, right? We don't want humidity to be all crazy. We want to make sure there's adequate airflow. With liquid cooling systems, we still have to check on the coolant, but it's not very intensive. This is kind of the level of your car. We're doing oil checks once in a while, it needs a yearly oil change. Coolant maintenance, for the most part, is a single year, small coolant extraction that gets taken out of the CDUs. We send it to a lab, we're looking for the propylene glycol concentration. In most cases, nothing is needed, and if it is, we ship back another highly concentrated vial of PGW, gets injected into the system, and that's it. So maintenance is quite low, but also it's so successful because we're using propylene glycol. But service is really one of the important parts of this that we always emphasize is HPE has a lot of different levels of involvement. So if you think about the big supercomputers, we are extremely involved. We have resident engineers. HPE badge staff are coming to the data centers and bringing the systems online, but also working with infrastructure teams in advance of the systems to make sure piping is correct, flow rates, water quality. But even across enterprise, different levels of customers based on their existing knowledge can be catered to based on what they want for agreements. 24/7 response or next day service. There's a lot of flexibility there. And so this is always something I like emphasizing. And then the final one is, what do you do with these systems when they're at end of life? HPE works with customers through that whole process. So I always want to reinforce that the partnerships are the big thing for us. Working with a partner like HPE and choosing that technology is more than just the hardware. It's how the product is built, how it's deployed, how is it serviced. That makes a really good customer story, and it makes you feel good investing in this kind of technology long term. So thank you so much for coming to the session.